In our previous unit of instruction, we looked at the structure of the atom and how electrons are arranged in the electron cloud. We're going to be using those concepts now to develop an understanding of how atoms bond together covalently, and that's what this lesson is about. So this unit, Unit 3, is about bonding, and we're going to relate the stuff we learned in the previous unit about atomic structure, orbital rotations, electron dot notation, to this concept of bonding. Okay? So yesterday we took just a little, not yet yesterday, that's right, the day before yesterday, we took a little time and talked about hybridization. I'm going to remind you about the hybridization I've already talked about, and then we're going to move on to different kinds of hybridization, and then how that hybridization affects how we think about bonding. And later, in fact tomorrow in this class, you're supposed to have some round balloons and long balloons, and we're going to make models of bonding so that you can see how these bonds actually appear in space. Because what we're doing right now is just pieces of things on paper that are ways of figuring out some things about bonding, but we're not going to actually show the shape of the bonds. We'll start to do that tomorrow. All right, so yesterday we talked about what's called Sp3 hybridization, and I'm going to use carbon here as the example. And so in the first primary level, you've just got one sublevel, S, and only one orbital, and there are two electrons there. In the second primary level, you've got two electrons in the S sublevel, but in the P sublevel, you also have two more electrons. And you put one electron in this orbital and one electron in this orbital. Remember, this is just a way of kind of keeping up with where all the electrons are. It's not what the orbitals or electrons actually look like. So when we hybridize this into what's called Sp3, so I'm just going to label it Sp3 here to show that's what this is dealing with, Sp3. We're going to take this single S orbital that happens to be in the second primary level. The second primary level for carbon is its valence level. The term valence means the electrons in the highest primary energy level. We're going to take the two electrons in the P orbitals, and we're going to take the three orbitals here and put them all together in what's called an Sp3. And it's an Sp3 because there's one S orbital and three P orbitals in the valence level. And that's just the way we number it and name it when we hybridize it. It's called Sp3 when you put them all together. So the lower energy levels, in this case there's only one lower energy level, 1s, they don't change in hybridization. It's only the valence level orbitals here, these upper level energy levels, upper level orbitals that are going to hybridize or change their shape and change their energy. But we're going to write them as all of them being as one thing, four orbitals together in this orbital notation. And this is Sp3. S because there's one S orbital that's part of this. P3 because there's three P orbitals that's part of this. Okay? And then this is in the second primary level. The valence level of carbon is the second primary energy level. And we're going to take all four of these electrons and fill them in these orbitals the same way we filled the P orbitals or the D orbitals, or if we were doing F orbitals. We don't in this class, but if we're doing F orbitals, you put one electron in each orbital and then go back and pair them up if necessary. So we're going to have four electrons, 1, 2, 3, 4, 1, 2, 3, 4 electrons. And that's the Sp3 hybridization, or one way of representing the Sp3 hybridization for carbon. So we're taking these electrons here in these orbitals. This is the unhybridized ground state valence orbitals of carbon. This is the valence level. It's its highest energy level. Whatever an atom's highest energy level is that atom's valence level. And we're hybridizing This particular hybridization is Sp3. And that's not the only kind of hybridization. There are lots of hybridization forms. We're only going to be learning about 3 of those in this class. All right, so the next one we're going to look at is Sp2. So I'm going to show you the original unhybridized set first. All right, so for an Sp2, this is meaning that we're only going to hybridize one s orbital and 2 of the p orbitals. We're going to leave one p orbital unhybridized. So we're going to only hybridize this s orbital and 2 of the p orbitals. Okay, so instead of putting together 4 orbitals, we're only putting together, well, I got to have one s that's unhybridized here. We're only putting together 3 orbitals here to make this kind of hybridization. And then this p orbital on the end over here is left unhybridized. So we're going to put it over here by itself. So we put the 2 electrons in one s. All the lower energy levels never hybridize. Only the valence level, the upper levels here that hybridize for bonding to occur. And you have to have hybridization to have any kind of covalent bonding. And if you remember from physical science, covalent bonding is the sharing of electrons. So this is an Sp2 set of hybrids. And this is a p orbital that's unhybridized. And both of these are still in the 2nd energy level. This is the valence level. That's where all this takes place. So we'll put a 2 out in front. So we're going to take all of these electrons in the valence level, and even though we've kept 2p separate, we're going to take all of these electrons in the valence level and put them in one orbital at a time and pair up as needed. Okay? So we're going to we have 4 electrons in the valence level. We put in 1, 2, 3, 4. So in this case, we're only hybridizing 1 s and 2 p's. So this is not the entire valence level, just 3 of the 4 valence orbitals. But we're hybridizing. And the hybridization we're doing here is Sp2. And the ones we're hybridizing are these, or making these 3 hybrid orbitals here. Which means that we have this orbital here that's left unhybridized. Which is basically unchanged. All right, so that's Sp2 hybridization. And the last kind of hybridization you need to know about in this high school chemistry class is called Sp. Again, I'm showing you the original unhybridized set of orbitals for carbon. And carbon is just our example. You can do the same thing with any element that goes through covalent bonding, and it's only the nonmetals that go through covalent bonding. There are actually some other elements that go through covalent bonding, but for high school we just about limit that entirely to only nonmetals. And 1s remains unhybridized. All right, now Sp3 means I hybridize 1s and 3 p's. Sp2 means I hybridize 1s and 2 p's. Sp must mean 1s and 1 p is what I want to hybridize. Okay, so only this orbital here and this orbital here get hybridized. Okay? So we're only going to put together 2 orbitals here. And we call this Sp. And it's in the second primary energy level, the valence level for carbon. So we show a 2 here. And we have p orbitals, 2 p orbitals that we left unhybridized. Okay? So these 2 right here just are left alone pretty much. They're not hybridized. Not going to change them. All right, we're going to put the electrons in here the same way we did previously. Count all the electrons in the valence level and the unhybridized set and put them in all of these orbitals as if they were one kind of set, like we did with P and D and F sublevels. 1 electron in each of the orbitals. And we don't need to pair any up, but if there are more than 4 electrons, we come back and pair up from the beginning. All right, now, let's remind ourselves something you probably should know. If you don't know, I'm going to remind you from physical science that it's only the nonmetals that go through this covalent bonding. And what we're doing now is we're learning more about this kind of bonding. In physical science, you learned that they shared electrons, and they are going to share electrons. But there's more to it than just sharing electrons. They not only share electrons, they're going to share these orbitals. And the reason they have to go through hybridization is they have to change shape and energy for this kind of sharing to take place. The original unhybridized set of orbitals can't bond in the way that we know that they do. Okay? So let's take a look at a simple bonding structure. Let's say we want to show how carbon bonds with hydrogen. This sounds like an example because it is an example. Yeah. Okay. So let's show this Sp3 set of hybrid orbitals here. 1s remains unhybridized and it's not involved in bonding. And then we've got the Sp3s and we've got 1 electron in each of the Sp3s. So the orbital notation for hydrogen is this. There's only 1 electron in hydrogen. That electron in the ground state is in the first primary level, and the first primary level only has an s sublevel and only has 1 orbital. There's only 1 orbital in any s sublevel, and so that 1 electron is just right there. In order for covalent bonding to occur between carbon and hydrogen, hydrogen is not only going to share its electron with carbon, it's actually going to share the orbital. 2 orbitals are going to become 1. 2 orbitals are going to become 1. They're going to, sometimes it's called overlap. Okay? Think about it like this if you want. You've got bubbles floating in the air. Okay? And so if you have bubbles floating in the air and they happen to run into each other, what does that look like? First of all, you kind of get something like this, don't you? That makes sense? And then they'll actually become 1 bubble. You ever seen that happen? Well, that's one way to think about what's happening here. It's kind of becoming one thing. Okay? All right. But now I have 3 more orbitals that are now available to bond with hydrogens, and that's exactly what happens. Let me go back now to our original unhybridized set of orbitals. If I were using these orbitals right here to bond with hydrogen, I would only have 2 orbitals available. It has to share electrons. You have to have 1 electron from one atom and another electron from another atom for that kind of sharing to take place. Well, carbon in its original ground state orbital notation only has 2 of those electrons in the correct arrangement. In order to have 4 electrons share in an orbital, we have to arrange these electrons in a different way, and that's in fact what they do. And that's what hybridization is about, arranging the electrons so that this is possible. So that's just one hydrogen. We've got 3 more places for hydrogens to share electrons and therefore covalently bond. So this is all possible. So now I want to draw it where I've actually put these orbitals together. So it's like this is a comic book. This is our first panel, and then we go to our second panel here. Okay. So here's carbon, and remember 1s isn't involved, but in 2sp3 I'm going to combine the 1 electron in each of these orbitals, and I'm going to combine the orbital itself with an electron from hydrogen. And so to show this, I'm going to have to put the hydrogens here kind of sideways. So I'm going to spin it 90 degrees for you and show you how I'm going to put the hydrogens in here. Okay. Now there's really no place for me to put that 1s for hydrogen. Okay. I guess I could have put it sideways too, but basically it starts to be a little bit hard to get everything to fit together when we're using orbital notation. But this is what happens in terms of, or in the sense that we're actually sharing these orbitals that we drew orbital notation for in the last unit. Okay? So you can imagine how much more complex it would be if we were using larger and larger atoms. Okay? So the problem is that you have to understand this sharing of orbitals takes place without being able to actually draw the orbital notation that would show it. Once you get past get into more complex atoms, it becomes more and more difficult to show it. Okay? So what we go to then is the electron dot notation. Electron dots now. So using electron dots then, carbon has how many electron dots around it? No, that's a total number of electrons. How many in the valence level? How many electrons does carbon have in the valence level? 4. Okay? And the reason that we put them one on each side of what is an imaginary square here is because we can do this hybridization here. If we go back to our original unhybridized set of orbitals for carbon, there's really only 2 electrons. And so if you were using this way of thinking about how electrons are arranged, we'd be writing carbon like this, where 2 of them are paired together and 2 are like that. And these 2 up here at the top wouldn't do any kind of bonding. So this isn't going to work for us. We're starting with the original, and hydrogen just has 1 electron in its valence level. It only has 1 electron total, but that's its valence level, and so it just has 1 dot. Okay? Now, if you remember from physical science, atoms want to have 8 electrons in their valence level. Okay? And so what we're going to try to use these dots for is to show how we share electrons to get those 8. Okay? Now hydrogen, because it only has the first primary energy level, and you can only have 2 electrons in the first primary energy level, it's going to have a full valence level when it has just 2. But carbon's going to want to have 8. And so we can share this electron here with this carbon, and now carbon has 5. And if we put another hydrogen around it, and we share these 2 electrons, now carbon has 6, and both these hydrogens have the 2 that they need. Keep on adding until carbon ends up with the 8 that it'd like to have. Yeah. Yeah. Well, you could only add 3, but that is not what happens. Carbon has to bond in a way that gives it the 8 it wants. You have to do something to figure it out to get 8. Right. Now there are exceptions to that. Okay, we will talk about some of those. There are rare cases where an atom only has 6 electrons when it does all the bonding it's going to do. You know, but that's another story for another day. Okay. Now this is just how we figure out how we can share electrons to give carbon all the valence electrons it wants and hydrogens all the valence electrons they want. So we're going to go from this to an arrangement that's a little more condensed. Okay? So what we're going to do is we're going to take this carbon atom and this hydrogen atom, and we're going to kind of squeeze them closer together. Okay? So if I have 2 dots like this, 2 electrons, and I squeeze them together, that's as close as they can get. And the 2 atoms are over here, okay, where my fingers are. Okay? And if I want to get them a little closer, I can do the dots like that, and now the elements will be a little closer together. Okay? You got that? All right. I'm glad y'all think that's funny. All right. Now, so here's what I'm going to do, guys. Instead of having the dots come together like this, we're going to come together like this. And we're going to put them over and under on this side. Okay? And up here at the top, to do the same thing, we're going to squeeze them together like this. And over on the side over here, like that, and over on the bottom like this. Okay? And this is called a Lewis dot formula. Okay? Listen, you're going to know Lewis like you just never thought you would in here because we're going to do a lot of Lewis stuff. Lewis is very important in chemistry. Okay. We got a Lewis definition of acids and bases and Lewis dots and all kinds of things having to do with Lewis. He's a Nobel Prize winner in chemistry. All right. Now, up here, this original stuff we drew without the circling, those were called electron dot formulas or electron dot notation. Once we did this, where we showed how they share, we got this really high-level name for this called the sharing arrangement. No, that's not a high-level name. It's just a descriptive name. The sharing arrangement. Okay? Sharing arrangement. All right, so if we were writing a comic book, this would be panel 1, panel 2, panel 3, and panel 4. Okay? 1, 2, 3, 4. This is, remember, all of our covalent bonding occurs between nonmetal atoms. So I'm going to let you choose 2 nonmetal atoms.
Oxygen, proton, neon, and carbon.
Well, first of all, noble gases don't bond.
Oxygen and carbon. Phosphorus.
All right, I've heard, among other things, phosphorus and chlorine. Okay? Let's do phosphorus and chlorine, okay? All right. Now what we're going to do is I want to continue to show orbital notation here, but after this example, the orbital notation is not going to be required. What you need to know is how we get from orbital notation to the electron dots But as this gets more complex, we're going to not show orbital notation every time. Okay, you need to know what it means and how we use it to get there. Okay? All right, so we said phosphorus and chlorine. All right, so phosphorus is this, and its orbital notation, 1s, and it's right here, so it's in the third primary energy level, and we need 3 electrons in p. Okay? 1s has 2 electrons, 2s has 2 electrons,
Take your time.
2p, 1 electron in each box or orbital, and go back and pair them up as needed. 3s has 2 electrons, and now we're at 3p, and p sublevels have 3 orbitals, and we need 3 more electrons, 1, 2, and 3. What I want to do now is to hybridize this to sp3. Remember, it's only the valence level, the upper level here, the highest energy level, that goes through this hybridization. And sp3 combines the s orbital in the highest energy level, the primary energy level called the valence level, and all 3 of the p's. All right, now we've got to combine all 4 of the valence level orbitals, and we're going to call this sp3. And in this case, the valence level is 3, so this is the third energy level. We're going to put 3 here. We're going to count all the electrons, 1, 2, 3, 4, 5, and put them in 1 in each box, and then we're going to have to pair up 1. And that's phosphorus. We need to do the same thing then for chlorine. Okay, so write the orbital notation for chlorine, and then write the sp3 hybridization for chlorine. Okay, let's see how you did.
I failed at everything. Uh-oh, apple food.
Yes.
I forgot what I was going to
How'd everybody do?
Good.
All right, let's look at the hybridized form then.
Wait a minute.
I asked what you wanted, sweetheart. All right, so we're going to combine all of the valence level orbitals here for sp3. And we've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. Booyah. All right. Sounds like you did good. Okay.
I don't feel like I'm ready.
We'll get lots of practice with this. All right, now, by hybridizing then, you can see that there are 3 electrons available to share, and phosphorus, and chlorine has 1. If we do the electron dot formulas, phosphorus has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and chlorine has 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 1 on each of the 4 sides of an imaginary box, then pair up to get to 7.
Wow. Look at that.
Okay? Now, these two electrons can share right here. These two electrons can share here. And these two can share right here. And lo and behold, both the phosphorus and the chlorines have all 8 electrons they want to have.
Well, I don't know what you're doing. Why did you Lewis Chapter?
Not yet. It's not Lewis yet. This is the sharing rate. We started with the electron dot notation or electron dot formula, and then we shared. So this is a sharing arrangement. How do we get to the Lewis dot formula? Squeeze everything together. Okay. So phosphorus, and we're going to squeeze this phosphorus with this chlorine. But the electrons have to be on the outside. You can't just get rid of electrons. And these two are being squeezed in between here. And these two electrons are going to be squeezed in right here. Okay, and this is a Lewis dot formula. Okay. All right, so we've got a Lewis dot formula, and I want to take this one more step now and show you what's called a Lewis formula. Okay? Well, we're going to get rid of some of the dots. Now, let me tell you this. This is the rule. Listen carefully. The difference between a Lewis dot formula and a Lewis formula is simple. Shared pairs, and only shared pairs, get replaced with lines. So let me tell you what a shared pair is. This right here, it's a shared pair because it's shared. It's shared between chlorine and phosphorus, okay? And how many shared pairs do we have here in this structure? 3 shared pairs, so we're going to replace 3 of those sets of electrons with lines, okay? So here's phosphorus, and between phosphorus and this chlorine, instead of a double dot, we're going to put a line. And between this phosphorus and this chlorine, instead of a double dot, we get a line. And between this phosphorus and this chlorine, instead of a double dot, we get a line. We have to put the remaining dots on there. So if they're unshared, there's another term. I'll write it out for you. I'll label it for you here in a minute. They're called, these dots that are left like this are sometimes called unshared pairs or lone pairs. Okay? One or the other is fine. No, not unless, you don't have to label it unless I ask for it, but I want you to know what they're called. Because as we do this more, and I use that term, or these two terms, or this term, I need you to know what it means. Okay? We need to be able to talk the same language, right? Okay? Now, listen up. Shh. Shh. These shared electrons form a covalent bond. So this is a covalent bond, and this is a covalent bond. Okay? When they're shared like that, they form a covalent bond. Okay? And, now we'll do more of this tomorrow, but whenever we have just 2 electrons that are shared like that, 2 electrons shared, is called a single bond. Okay, 2 electrons shared is called a single bond. And in this drawing here is a Lewis formula. The whole drawing all together is a Lewis formula. We did not draw a Lewis formula for this, remember? So why don't you guys do that right now? And we'll see how you do.
So another name for
How'd you do? Okay? So this is our Lewis formula. Okay? Okay, let's step it up a notch.
No, Mr. Pattern, I haven't even conquered the first notch. Double bonding? Really, sir?
Double bonding, really? Yes.
I think you be forgetting that we're high school and not college. So you be going fast like we're in college, but really we're in high school in the 11th grade.
Okay. We're going to use a really simple molecule to start with. Okay? We're going to start with O2. We could start with hydrogen, but that's a little more simple than I want to do. Okay? Now, in the previous example, we used Sp3 hybridization. For double bonding, you must use Sp2 hybridization.
So for regular bonding, we use S3.
For if you have nothing but single bonds, it's Sp3 in almost every case. But for double bonding, you must have Sp2. There's a rare case, one case we'll tell you about later, where you have some Sp hybridization for double bonding, but that's a special case. Okay? For double bonding to occur, Sp2 hybridization is required. So here's the Sp2 hybridization for oxygen. Actually, I've got to combine that one, don't I? It's supposed to be 2S. Well, I can do that. I can go with that. Well, actually, I put an extra orbital on there. It should be separate. That last one should be a P off by itself. So if you fill up the orbitals the way you were taught, you're going to put 6 electrons in the valence level, and you put 1, 2, 3, 4, then come back and pair up 5 and 6. Okay, and I need another one because I'm going to put 2 of them together. That subscript there means I have 2 oxygens bonded together. I hope you remember that from physical science. The subscripts mean you have that many atoms in that formula. So H2O means there's 2 hydrogens and 1 oxygen. So to show you what's going on, we're going to write another Sp2 hybrid set of orbitals.
It's not like somebody sleeping.
Now, okay, so before these unhybridized orbitals can share electrons, before these unhybridized orbitals over here can share electrons, you have to have hybridized orbitals sharing electrons. So these 2 orbitals, you could say they have to bond first. They have to share electrons first. That's not really what happens, but you can't do the second bond unless this one is also there. Okay? So we can say this is first, but you need to know that's not really first in terms of this happens and then the other happens. Okay? It's first in that, only that, you can't do this one unless this one is also taking place. So we can say this set here, the 2 unhybridized p orbitals, can share electrons, but only if we also are sharing electrons in hybridized orbitals. Okay? Now, just to give you a heads up about what's coming, This bond here between hybridized orbitals, bonds between hybridized orbitals are called sigma bonds. Bonds between hybridized orbitals are called sigma bonds, but bonds between unhybridized orbitals, or covalent bonds between unhybridized orbitals, are called pi bonds, just like pi in math, not like the pie you eat for dessert. So to be clear, all of these bonds right here were between hybridized orbitals, so all of these are sigma. All of these bonds right here were between hybridized orbitals, so all these are sigma.
Only the ones with the line.
Only the ones that come from unhybridized orbitals are called pi. The bonds or sharing of electrons between hybridized orbitals are going to be called sigma, and we'll find out more about that when we get to the models.
So that was the fourth name you were talking about?
Yeah, that was the one I was alluding to. We get to. Okay, all right. Now, if we're going to combine two oxygens together, and we're going to use electron dots, how many electron dots do you put around an oxygen? Well, look at your periodic table. It's right here. 6 dots. 1, 2, 3, 4, 5, 6. And so if we're going to combine one oxygen with another, then we need another oxygen here. 1, 2, 3, 4, 5, 6. Now, when I bond these two oxygens, I'm going to allow that oxygen, both these oxygens, to get to 8 valence electrons, because I can share this electron and this one. There's your double bond. 2 sets of electrons shared, 2 pairs that are shared, create a double bond. All right, remember this was called an electron dot formula, and now we have what's called a sharing arrangement. We haven't gotten to Lewis yet. Lewis means we're going to squeeze the electrons in between, and there's a little bit of a difference in how we do this for double bonds. For double bonds, you put them in this 4 corners of a box arrangement. Okay? And the lone pairs get left out here. So we're going to call this a Lewis dot formula. And if you remember me saying so, anytime you have a shared pair of electrons, when you write the Lewis formula, you can replace that shared pair with a line. Since we have 2 shared pairs, we're going to replace it with 2 lines. Just to make sure we're emphasizing this as much as we can. Sharing arrangement, Lewis dot formula, Lewis formula. Now what the Lewis formula doesn't show is the difference between the sigma and the pi bond. There will be a sigma bond, there will be a pi bond, but we won't see that until we get to the actual shapes when we make models. Okay? But there is, if there's a double bond, there's a sigma bond and a pi bond there. Okay? Let's go to triple bonding.
Oh my God, we don't even understand things.
Okay. Let's write the Sp hybridization for nitrogen. Okay, now nitrogen also combines 2 atoms of nitrogen together. Okay, that's called a diatomic element when you have only 2 atoms bonded together. But if you're going to have triple bonding, Sp hybridization is required. So if we're going to show Sp hybridization, the unhybridized form of nitrogen is this. Now you write the sp hybridization based on what I showed you previously. All right, so the hybridization of a nitrogen into an sp form. 1s doesn't hybridize because it's the lower energy level. We're going to take this S and this P and hybridize it. So we're going to join them together. And so this is SP. 1S and 1P makes SP. It's in the second level. And then we've got two p orbitals we didn't mess with. We didn't hybridize those. So they're going to be together over here, and this is 2p. And we count all the electrons, 1, 2, 3, 4, 5. Put them in there one at a time, and come back and pair them up as needed. Now then, we said that in order for pi bonding to occur, you also have to have a sigma bond. So the first bond, we could call it first. They can all happen simultaneously, but in order for pi bonds to occur, you also have to have a sigma bond. And sigma bonds only occur between hybridized orbitals. So these are the hybridized orbitals. This is where our sigma bond is located. Okay? And both of these, where we share electrons in these orbitals over here, in the p orbitals, the unhybridized p orbitals, those are going to form pi bonds. Okay? Now then, for electron dots, I'm going to give you a chance to practice. Write the electron dot notation for a nitrogen and another nitrogen. And then we'll show how we share electrons.
Pause the video.
So, nitrogen needs how many electron dots?
4.
5. Nitrogen has 1, 2, 3, 4, 5 valence electrons.
Like this, Mr. Can you count the last 2 boxes? Count what's in the last 2 boxes? 1, 2, 3, 4, 5.
You could, yeah. You're talking about if you could count these? That's exactly right. 1, 2, 3, 4, 5. That's how you
No,
get
I'm
5.
talking about
Really?
right here. 1, 2, 3, 4.
You can do that
1,
too.
2, 3, 4, 5. Yeah.
You can do that too.
Thank you. Sorry. I need to show them so they can understand.
You know you're not going to get residuals for that, right?
I'm not getting what?
Residuals. All right. Can y'all, can you show me how I'm going to share electrons there?
Oh, you're going to compare them. You're going to do the arrangement.
Show me. Show me the sharing. No, not up here. Do it on your paper. 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 Don't wait for me to do it. Do it for yourself. All right, so these are electron dot notation or electron dot formulas. We can share electrons in such a way that nitrogen has 8 electrons each. There's the sharing arrangement. Okay? All right, remember when we shared 2 electrons between 2 atoms, we had them over under here. When we shared 4 electrons, we made that kind of box shape. When we show them sharing 6 of them, we do it like this.
Wait, hold up now. Now you're trying to tattoo with you stuff. Because it's 3, it's that part of the video.
All right, so we have
Oh, the video going?
3 sets of electrons, 3 pairs of electrons. This then is called a triple bond. Okay? So the type of drawing is a Lewis dot formula. But this Lewis dot formula includes this triple bond. Okay? And this 2 pairs of electrons up here that are shared between these 2 oxygens, that's a double bond. See if you can do the Lewis formula for yourself. If you get it wrong, it's okay. Do it in pencil. It's not that hard. We can fix it. But see if you can figure out what the Lewis formula would look like. All right, we're going to have a guest teacher here who's going to attempt to do the triple bond Lewis formula.
Hi, how are y'all? Alright.
I left the grade looking for you.
I'm sorry that she's mad that I understand. She understands.
You did well.
Thank you.
All right?
Thank
You
you.
did good. That's the triple bond.
Wait, this one I'm gonna do right. I'm gonna come back tomorrow. I'm gonna do so much knowledge. I do this. Cause I'm gonna get on YouTube. Homework for me.
All right. Remember, the subscripts mean that's the number of atoms. So this formula means that you have 2 carbon atoms and 2 hydrogen atoms. And this is like solving a puzzle, guys. You've got to be able to just put your Lewis dots, sorry, let's start with electron dots. You've got to write your electron dots and try it in different ways until it all works out to get 2 carbons and 2 hydrogens together so that the carbons have 8 valence electrons and the hydrogens have 2. And this one, you're going to put them together. You've got 2 carbons and 4 hydrogens. Put your electron dots and the electron dot formulas there around the carbon and the hydrogens, and keep doing the sharing arrangement in different ways until you figure out how it will go together so that the carbons have 8 valence electrons and hydrogens have 2. And this is 1 carbon and 4 chlorines. And both carbon and chlorines need 8 valence electrons. Okay, so just keep working at it until you find the right arrangement. Okay. So, how many electron dots do you have around a hydrogen? I need let's see, let's make it H2O, H2CO. 1 dot around hydrogen. How many dots do we put around carbon? 4 dots around carbon. Because that's the number of electrons in the valence level of carbon.
How? Is that on the periodic table?
Yes. How many dots do you put around oxygen?
6.
Now, can you share these in a way that gives the carbon and the oxygen 8 and the 2 hydrogens 2?
She deserves it. It's only right. You gotta learn her lesson.
What you gotta do? Okay.
Then you just write the Lewis dot formula. This is the sharing arrangement. This is the Lewis dot formula.
Turn up. Turn down for a while.
And then you write the Lewis formula.
The Lewis formula?
Wow, that's crazy how I understood the first, 45 minutes class, and then it's all like, I'm done now.
Exactly. See, when we started, I was here. Yeah, bro, I was saying, so. Now I'm somewhere with, way back there. Yeah, I can't, I'm in the
We didn't learn, we did not learn this part.
I'm in the teacher prep room. That's not where I'm supposed to be. You know.
So let's see, how many electron dots do you put around a nitrogen?
2.
Nitrogen, you put around 7.
Is it not 2?
5.
5.
Why 5? Oh,
How many dots do you put around a hydrogen? And you combine those in a way that gives the nitrogens 8 electrons and the hydrogens 2. Yes, you can. You have to do it like a puzzle. Try it one way. If it doesn't work, try it again. Yes, you're making it hard.